Welcome to another edition in this series of videos, kind of recontextualizing some Professor Lewin physics videos, introduction style. So where we left off, I wanted to do a little bit of explaining of what I think is sort of being left out of some of the jargon. Oh, great. Oh, there. It's not that much better. Anyway, lighting, complex. So there's this idea they were using of dipoles, and so you have things that have independent charges, clean charges. It's just all positive on a surface, like the proton and like the electron. So you could do a balloon that kind of behaves like a proton, or a balloon, that's kind of like an electron, or a metal ball, or whatever surface you're using to hold the charge. And only certain surfaces will do that. And when they're independent or by themselves, we just call them a charge. When they're near each other, close, they use the word dipole. I mean, they put an insulating stick between them and say, there, I've now created a monopole. So these would be the dipoles, the monopoles, I'm sorry. Individually, they're monopoles. Together, they call them a dipole. And there's different rules about how that force survives as it. See, they don't really recognize the force, and they mislabel it. It's only one force, and it's magnetism is what I think it's appropriately called, that emanates from these charges. There's no two forces. There's two kinds of force, don't get me wrong. There's the force that a positive charge emanates, and there's a force that the negative charge will emanate, but they are not two different kinds. There's not two kinds of those forces. There's not the electric version and then the magnetic version. There's just one, and I think it's appropriate to call it magnetism. And the catch is that if I just have this red one, so let's just pretend this doesn't exist, then you can sort of understand that the only thing it's very clean, it's just red. And if I have a negative charge over here, it's just going to be doing this kind of thing, and it's all very clean. It's only one kind of force against another kind of force. They'll attract or they'll repel. Say it's two electrons, you could just see it's going to be all brown force. There won't be any of this messy red stuff polluting it. And the problem with a dipole is they're polluted. So when you make an artificial dipole, you're essentially taking one end of a magnet, the north end, and you're kind of even though your separation might be small, it's a separation. You're separating the two poles of the magnet, and calling it a dipole because you put a stick in here. Well, that really changes how the magnet functions, because when it's a magnet, you can sort of understand that there's going to be lots of mixture of force in this area. There's going to be lots of force coming off the red and off the brown that are going to both be coming in some point. There's going to be lots of mixed force. There's going to be space is going to allow more and more mixture as they travel through space, and so only at these extreme ends are you going to have pure force, and in the bulk of the area you're going to have this mixed force. So the point being that if you're measuring it by testing it with a compass needle, well, that's a monopole. A dipole. Okay, it has two poles. And if you're testing it with charges, that's a different test. And so the whole point I'm making here is that's why there's a difference. So when they say this is the 1 over r cubed for the dipoles, that only really is true when the dipoles are very close. The further apart I put the poles and create basically monopoles on a stick, then I revert to the 1 over r squared in terms of how the force diminishes, how the force weakens. So magnets only weaken, okay, based on the fact that, more rapidly, based on the fact that they are you can't break magnets in half and put a north end and a south end. Now you can take magnets and hold them in positions that make them a little more effective in terms of separating the poles. So you could take two different magnets and you could put them at opposite faces. And the advantage is now you're separating these two from these two in terms of their ability to affect each other, but it's still not very far away. So even though, see, the point would be is this repulsive force between the two browns goes right through this red thing, so the red thing doesn't block this repulsive force entirely. Well, that's another. It doesn't. Point being that you really can't simulate in an effective magnet, one that you use, the separation of the poles, and not in any clean way, because magnets always are dipoles. So that's the catch. I mean, technically these single monopoles are magnets, but they're not like magnetism, which is created because a whole bunch of atoms inside of something flip. Charge is only a surface phenomenon, and it doesn't have any depth, and so it's hard to create a magnetic monopole, even though these technically are, but they're only technically. So I'm just saying you can't write any hard rule. So as I've often said, these are tendencies. The r squared is a tendency, r cubed tendency. It's not a rule, and especially when you start bringing things very close together, the rules completely break down, because you could sort of understand, especially in magnets, if I bring them really close together, none of this bottom energy is going to get to the top parts, and none of this part's going to get to that, and it's going to be very segregated again. It'll be very clean, and it's only when I start to separate them that you get all this dirty stuff where the black and the red force mix. So at close, the rules get really weak as laws. I think it's enough. See what the difference is without the light. Yeah, the light's doing absolutely almost nothing. It's almost better without the light. Thank you. Jeez. Go figure. Now that was unintuitive. Oh, it looks better without the light. Totally unintuitive. So obviously I have the light in the wrong direction or something. So I have this stupid, for 2 weeks I've had this pain in the neck light on my table, and really hasn't been doing the job. Alright, so to the video. So this is the third lecture, part one of it.
We're going to work on a whole new concept, and that is the concept of electric flux. We've come a long way. We started out with Coulomb's law. We got electric field lines.
Okay, I would argue also that this idea of flux is another made-up kind of term. It really doesn't describe anything but how much of those little force bits, and they're force bits. They're not photons because they don't have a frequency, but they are photons in the sense they're made of the same thing photons are made out of. So they're real force. They have a real impact, and because there's two kinds of them, electron force and proton force, they will affect a positive or negative charge inversely. So flux is just measuring how much of that red and black energy gets on a surface, or gets in an area, or hits something. But there's no electric flux. It's still magnetic.
And now we have electric flux. Suppose I have an electric field, it is like so, and I bring in that electric field a surface, an open surface, like a handkerchief or a piece of paper. And so here it is. Something like that. And I carve this surface up in very small surface elements, each with size dA, that's the area, teeny weeny little area, and let this be the normal N roof, the normal on that surface. So now the local electric field, say at that location, would be, for instance, this. It's a vector. The electric flux, d phi.
So this is really getting into the calculation of how a surface charges. Okay, this is in some sense a description of the consequences of its induction through the process of being exposed to the force. So it's exposed to the force, and the force will, based on how the structure of the shape of the thing, will in certain places point in little subtle different directions. And overall, so if somebody's tugging on you, pulling one direction, pulling a little this way, pulling a little this way, there'll be a net, complete force on the whole entire surface or object. So I think that's what this is getting to. And it doesn't get it into it in any way that I particularly care for in terms of the symbols. A d phi, for example. What's a d phi?
That go through this little surface now is defined as the dot product of E and the vector perpendicular to this element, which has this as a magnitude dA. Now our book will always write for NdA simply dA. So I will do that also, although I don't like it, but I will follow the notation of the book. So this vector dA...
Be kind of interesting if you would just tell us why the n is important, but I guess that's just because the n has the little hat on it, which means it's a vector, and so it's pointing, and so it's making that clear, but the arrow over the top seems to be the replacement for the little n thing. I really don't want to get into the mathematical jargon, but it just seems like jargon.
It's always perpendicular to that little element dA, and it has the magnitude dA. And so this, since it is a dot product, is the magnitude of E times the area dA.
So dot product, I think, just means it's the product of, you have to do an integral over the whole thing to figure out the whole thing, the net.
Times the cosine of the angle between these two vectors, theta. And this is scalar. The number can be larger than 0, smaller than 0, and it can be 0. And
so another way of saying that might be that at the individual point there's going to be a vector, and then there's the net vector, and then you have a difference between the two.
Can calculate the flux through the entire surface by doing an integral over that whole surface.
Sort of what I said.
The unit of flux follows immediately from the definition. That is newtons per Coulomb. So the units of this flux is newtons per Coulomb times square meters. But no one ever thinks of it that way. Just SI units.
Right. I don't know how they're supposed to think about it. But I suppose the point would be is there's a net force and it has a strength of some, horsepower.
Give you some intuition for this flux by comparing it first with an airflow. These red arrows that you see there represent the velocity of air. And you see there a black rectangle 3 times. In the first case...
you probably can't see it because I can barely see it. So it's a flow of air, and you're just taking a square, and you're sticking it in this way, and you're sticking it in this way, and then you're sticking it in this way at an angle. And you're just saying how much stuff gets through it.
Notice that the normal to the surface of that area is parallel to the velocity vector of the air. And so if you want to know now what the amount of air is in terms of cubic meters per second going through this rectangle, it would be V times A. It's very simple. However, if you rotate this rectangle 90 degrees so that the normal to that rectangle is perpendicular to the velocity vector, nothing goes through that rectangle, and so it's 0. So now,
kind of obvious. You know, it's like turning yourself to avoid something hitting you, and so you make your profile smaller. So it's this versus this. Yeah. And then he's just going to do the in between.
now the flux, if you take it, air flux is 0. And if the angle is 60 degrees, then it is, of course, V times A times the cosine of 60 degrees. Now think of these red vectors as electric fields. So now the electric flux.
Now the difference is that now you're just going to basically say which way will it push you. So obviously if you're perpendicular to the force, you'll be moved quite perpendicularly. If you're vertical to the force, you won't be moved. And if you're canted to the force, you do this. So, yeah, kind of basic.
Going in the first case through that surface is now simply E times A.
A little volume,
In the
I
second
think.
case it's 0. And in the last case it is EA times the cosine of 60 degrees. So you can sometimes think of this as airflows. We also saw that when we dealt with field lines. It can come in sometimes very handy.
Analogy is always a little bit dangerous, or simplifications as stated. You know, you can call two charges on a stick a dipole, but it really isn't.
I now take a surface which is not open as this one is. This is an open surface. Come in from both sides. But now I choose one that is completely closed, like a potato bag or a balloon. I'll put this line in here to give you a feel that it's a completely closed surface. So you can only get inside if you would penetrate that surface from the outside. And so now I can put up here and here these normals, dA. And there's another normal here, maybe in this direction, dA. In this case, by convention, the normal to the surface, locally to the surface, is always from the inside of the surface to the outside world. It's uniquely determined because it's a closed surface. Here, it was not uniquely determined.
Okay, so I don't really understand sometimes what the point of this is, but apparently we're talking about something that contains a charge, and then we're putting a bag, and the charge is radiating. And so there are certain places, in certain locations, the charge will come out. If I put a hole in certain places, it'll come out in certain directions. Something like that.
I arbitrarily chose this one, but I could have flipped it over 180 degrees. Since it's an open surface, it's ill-defined. Here, it's never ill-defined. So the normal is always chosen both from the inside to the outside.
You could sort of understand it as if you put a dipole, two charges of opposite inside, then the little surface bits would magnetize in certain directions relative to that. The compass needles would line up in certain ways, and that would decide what vector the outside surface interprets the inside surface. That's one way of interpreting what he's talking about. The other way is just saying, I want to just capture the charge. And so that's, I think, where this is going, is this is just saying, what's the total charge the thing's radiating? Well, if I want to know the total charge in some way, in terms of what it's producing for the whole universe, I have to put a bag over it and catch the entire charge. But if it has symmetry, if it's symmetrical, then I don't really have to. I could just take a circle around it, and once I have that, I just turn the circumference number into the area number and calculate it that way. I think that's where this is going.
And now I can calculate the total flux going through this closed surface, locally multiplying E with dA, dot product, over the whole surface, out comes a certain number. And that is now therefore the integral of E.
Alright, so that's, he's talking about capturing it, and we'll just leave it there. I think that's what he's talking about. So he didn't put anything inside that bag, but I think that's what he's talking about.
Dot dA integrated over that closed surface, and since it is a closed surface, we put a circle here to remind us that it is a closed integral. And here in this case, it is a closed surface. And this now is the total flux through that surface. It could be larger than 0, It could be smaller than 0. It's a scalar, it's not a vector. It could be equal to 0. If it's equal to 0, then you can think of it, whatever flows in, if you think of it as air, also flows out. If more flows out than flows in, then it is positive. If more flows in than flows out, it is negative.
All right, so that makes it a little more complicated because he's got 2 arrows going out. He doesn't have any of this flowing in stuff from anywhere. So, but in a sense, from his description, he's talking about equilibrium. So you could think of it as a bag where you blow it and it has a hole in it, and the bag will fill up with some pressure, and then once it has its equilibrium pressure, whatever goes in goes out. I don't know. Could be.
So let's now calculate the flux for a very simple case where I have a point charge. So here I have a point charge, and I'm going to put a bag around this charge, and the bag is a sphere. It is a sphere, and the sphere has radius capital R. And let this charge be plus Q.
So now it's a sphere, it's not a bag. He says it's a bag, but it's really not a bag, right? I don't know. He didn't draw a bag, so I don't know.
Just for simplicity. Well, I pick a small element dA here.
I mean, he did say sphere, so sphere should be 3-dimensional. So he's put a 3-dimensional thing around a 3-dimensional little thing. So the charge is now covered by so it's captured. Good enough.
And that element dA is radially outward. dA. This is the normal to that surface, so that is radial. The electric field at that point is also radial. We have dealt with that before. So the A and E, not only here, but anywhere on the surface of this sphere, are parallel. So the cosine of the angle equals 1.
Right, so it's just basically saying his little circle is the same as a big circle, so everything that was going in a certain way stays going the same way because you haven't changed anything. And basically it doesn't say much, except you can sort of understand that if you're closing the entire thing in, you're going to capture all of the force. It's essentially going to go through the surface. So there's no diminishment. No matter how big or small I make the circle, as long as it's bigger than that point charge, it'll have exactly the same amount of charge on it. Now the charge density will change, but it'll capture as much, the same amount of charge will be captured. I mean, it's kind of obvious. It's like making a glass globe and then putting something in it that does something. It's contained inside, and so all the energy has to hit the exterior.
I can also introduce here the unit vector R roof, which is the unit vector going from capital Q to that element where I evaluate the teeny weeny little amount of flux. So if now I want to know what the total flux is through this sphere, it's very easy. Because since this is a sphere, the E vector in magnitude is everywhere the same, because the radius is the same distance to this charge, and dA and E are parallel. So it's simply the surface 4 pi r squared of that sphere times E. And so now I have that the total flux through that closed surface is simply 4 pi r squared times E. Well, what is E? The electric field at this distance r.
Again, it's the magnetic field, but whatever. It's going to be a forever problem.
Equals Q divided by 4 pi epsilon 0 r squared times r roof. That gives me the direction. And so, if I know that the flux is 4 pi r squared times E, I put the 4 pi r squared here, I lose the 4 pi r squared, and I find that the E vector, at least the magnitude of the electric field, that the flux, phi, that's what I want to calculate, I multiply this by E, equals Q divided by epsilon 0. And this is independent.
So epsilon 0 is a constant that has something to do with the permutivity of space. So it's the charge divided by the permutivity of space, which is like a zero number, something like that. I don't know.
Of the distance r. And that's not too surprising, because if you think of it as air flowing out, then all the air has to come out somehow, whether I make the sphere this big or whether I make the sphere this big. So the flux, being independent of the size of my sphere, the flux is given by the charge, which is right here at the center, divided by epsilon 0.
So I don't know how it's very helpful, but so again, the point is that if you put a small charge on a large surface, it's not going to make the surface, it's not going to have the same charge density, so it's going to dilute the charge, the pressure.
Now, if I had chosen some other shape, not a sphere, but I had dented it like this, it's clear that the air that flows out would be exactly the same. And so I don't have to take a sphere to find this result. I could have taken any type of strange closed surface around this point charge, and I would have found exactly the same result.
The problem is if you use something misshapen, you can't use the cheats of symmetry. So the cheats of symmetry essentially are, there'd be a vector in the middle, and you can sort of understand that every single other vector cancels because it's round. So there's always a left and a right from every point. And all of those essentially will be opposite vectors in the dimension space. And they'll cancel to this. They'll always average to this. So the straight line, one line, on a sphere is essentially the only line you need to know, because all the other lines cancel out. I mean, all the other lines average to this.
And if I put more than one charge inside this potato bag, then clearly, since I know that electric fields from different charges can be added, should be added vectorially, it is clear that the relation should also hold for any collection of charges inside the bag. And therefore, we now arrive at our first milestone in 802, which we call Gauss's law.
All right. Now the problem with that is, again, see, these are all very conditional statements. So when he's saying I put any number of charges in, they still have to be symmetrical. So he has to have them equally balanced. If he puts imbalanced charges in, none of this holds, because then different parts of the surface will have different pressure.
And Gauss's law says that the flux, the electric flux, going through a closed surface, being the closed surface of E dot dA, is the sum of all charges Q which are inside the bag that you may choose at any time you pick that bag, divided by epsilon 0. And this is the first of 4 equations of Maxwell, which are at the heart of this course.
Right. So it's just, you're just saying dA is the area of some piece you took out of it, and you just whatever the the closed surface. Oh, it's an integral. So you take a dA, and then you have to recognize what your dA was part of. So you just say, what percentage of the sphere have I calculated, and then approximate that over the whole surface. But like I said, if you use symmetrical surfaces, you don't have a problem. As soon as you do something non-symmetrical, this formula breaks down. So it's completely dependent on symmetry, that is, balances. If you have imbalance in the bag, this ain't going to help you much.
So the electric flux through any closed surface is always the charge inside that closed surface divided by epsilon 0. And if that flux happens to be 0, it means there is no net charge inside the bag. There could be positive, there could be negative charges, but the net is 0. Gauss's law always holds, no matter how weird the charge distribution inside the bag, no matter how weird the shape of this bag, it always holds.
All right, so I guess I have to restate what I just stated, because you just basically said no. Yeah, you can have the charges any shape. that's again if you're just doing the net. So that's just if you're not going to put a hole in the bag. If you're going to put a hole in the bag, you're going to have a difference. So that's, just make that clear. If you're just saying the entire surface will be hit by a certain amount of charge, and as long as the surface is a conductor, it will distribute that charge evenly, fine, you don't have a problem. But if you don't have a surface that will do that, you'll have a problem.
But Gauss' law won't help you very much if you don't have a situation whereby the charges are distributed in a very symmetric way. Gauss' law holds, but it doesn't do you any good.
Okay, so we're back to what I said. So he said, it doesn't matter where you put the charges. Well, it does matter. So one minute he says it matters, doesn't matter. Doesn't really matter to me. Yeah. I don't know exactly what the point of all this is. So I don't know why this Gauss's law is so Gaussy important. I don't know its entire function, except to understand that the shape of a surface is really important. So you could sort of use it for the argument that inside, like if you did the reverse of what he's doing, thinking about from the inside out, and thought about it gravitationally from the outside in, you can understand that if you do make a hollow Earth, that there wouldn't be any gravity inside. And there wouldn't be any gravity inside, not because there's no gravity inside, not because the force isn't getting there, but because it's like the moon argument. There's a point where the two balance. And when you have a sphere and you go inside of it, every time you move this way, you expose yourself to more force from this direction and less of this direction. So the amount of the circle you cut off, the closer you get this angle, okay, it gets smaller and smaller and smaller. So you're exposed to a smaller amount of energy at one side, and the other side is hitting you with more energy. Now this energy has to go much further to hit you, but there's more of it. So it's completely proportional. No matter where you move inside the sphere, you're always changing, you're cutting more pi behind you, behind the direction you moved, and less pi in front of you. So even though you're moving closer to a force, a surface, okay, you're exposing yourself to more surface from behind. So there's more snipers that can hit you from behind, even though the one in the front of you has a real good bead on you. So the odds of getting shot are still the same. So no matter where you go, your odds of getting shot are exactly the same. I think that's where this is going.
If you want to calculate the electric field. In order to calculate successfully the electric field, you do need forms of symmetry, and there are three forms of symmetry that we will deal with in 802. One is, of course, spherical symmetry, another one is cylindrical symmetry, and a third one is flat planes with uniformly charged distributions.
Okay, so the trick is all of those, the two lather ones, don't have the, see, spheres don't have an infinity problem because they're closed. So, no problem. The others do have an infinity problem. So cylinders, this is only, a lot of this stuff is only going to be true for 99% of the cylinder, and at the two ends, it all falls apart. And for flat planes, yeah, it's only true as long as the plane is much bigger than your point charges. But as soon as your point charges become something substantial, your charges, it all breaks down. It's like infinite planes make sense, you know, in this way makes sense, because you're thinking about little atoms, and atoms on a surface become sort of infinite to some point. You know, it doesn't take much bigness to say, oh yeah, there's a trillion of them there, so I might as well just forget about the fact that they're that they're anything other than an infinite distance from the edges, because they almost are by practically they are.
We also have situations of symmetry. And so now I would like to, as a first example, use an application of Gauss's law, and I will start with a situation of spherical symmetry. And I use a thin shell, a hollow sphere, which is thin.
Alright, so we've sort of gotten to, we're getting to he sounds like he's heading for the Earth example I just gave, a hollow Earth. I don't know how thin it has to be, but regardless, I mean, it really shouldn't make any difference.
So this radius is r, and I put charge q on here, but it is uniformly distributed. That's crucial. If it's not uniformly distributed, I have no symmetry, I can't do the problem. So it's uniformly distributed.
Yeah, which is just another way of saying it's a conductor, or it's another way of saying, like gravity example, it's coming from all sides, so there's no other thing messing with the force hitting the surface, and therefore it's even.
We will learn later in the course that it's very easy to do this, because any conductor of this shape, if you bring charge on it, will automatically distribute itself uniformly.
And this is another place to bring up the point that when he was making the dipoles and moving the things apart, that's exactly what he was relying on, is that when he separated them, as long as you separate them quickly, what they were, that is, they were unevenly charged, in the sense that one side of the sphere had a very proportionally plus or minus. That charge automatically becomes averaged into one symmetrical charge that is somewhat lower than that extreme condition.
We have the charge plus q on there, uniformly distributed, that's a must. And I would like to know now, what is the electric field here, at a distance r from the center, and what is the electric field here, at a distance r from the center. In other words, I want to know, what is the electric field everywhere in space, just due to this charged, uniformly charged sphere. And with Gauss' law, just goes like that. You now have to choose your Gauss surface. And if you don't choose it in a clever way, you get nowhere. In a case like this, I would think it is rather obvious that the Gauss surface that you would choose are themselves spheres, concentric spheres.
So let's understand, this Gauss's law has got integrals in it, so it's not exactly simple, unless you know how to do an integral. But it's just basically telling you that once you have some kind of solid geometry, you can find out one piece of that thing and just multiply it because it'll be even. So it's just basically saying that all you need to do is calculate one vector and you got all the vectors, in a sense.
You want to know what the electric field is at this point, you choose a sphere with this radius r going through that point. If you want to know what it here is, you choose a sphere going through that point. All the way enclosed. It's a concentric sphere. And now, you have to use symmetry arguments. And the symmetry arguments are the following. Since this is spherically symmetric, this problem, if you're here, whatever the electric field is here in magnitude must be the same as it is there, and it must be the same as it is there. Because of the symmetry of the problem. It couldn't be any larger here than it could be here. That's obvious. That's a symmetry argument. Because the charge here is uniformly distributed.
So again, he's using spherical symmetry, so again, it's this argument that there's just one, and you can pick the one direction anywhere, and everything else on the sphere will average to that normal. So that's all you need to know, because everything else cancels out in a sense.
That's symmetry argument number one. Now comes another symmetry argument, and that is the electric field, if there is an electric field, must be either radially pointing outwards or radially pointing inwards. So either it has to be like this, or it has to be like this.
Depending on whether it's a positive charge or a negative charge. So, yes. What do I want to say about that? Nothing.
And here the same, either like this or like this. Because we already know if this is a positive charge, that it's going to be pointing outward. It cannot go like this or like this, because nature could not decide in this spherically symmetric problem to go like this or like this. It can only go radially. That's the second symmetry argument. So now, if we go to this sphere now, and we know that E is radially outwards, apart from a plus or a minus sign, apart from the fact that the angle between dA and E could either be 0 degrees or 180 degrees, we know now that the surface area of that sphere, which is 4 pi r squared, times the magnitude of the E vector right here, I can do that now.
Okay, so let's understand again. The thing that's charged is the Q circle. That's the charge. He's doing a point in the center or inside that sphere. originally in the center. But again, it doesn't matter where you go, you're going to get the same answer on the inside, which is nothing. Because again, the forces are going to equal out. The closer you get to the surface on one side, the more you expose yourself to the circle on the other side.
Because the A and E are either parallel or anti-parallel, that must be equal to Q inside divided by epsilon 0. There is no Q inside, so E must be 0. That's an amazing result. You say.
So, I don't know exactly how he got there's no Q inside from what he said, so, yeah. But the point is there is none. Yeah, that's right. The charge, like I said, because of the symmetry in the terms of you're going to get hit by more stuff from behind you, the closer you get to a surface, you're exposing your backside to more impacts. Even though the impacts coming at you are getting stronger, you're getting more from behind you, and that'll always happen no matter where you go.
Okay, well, there's no charge inside. Still an amazing result, because it means that anywhere inside here, no matter what radius you choose, the electric field equals exactly 0.
Alright, so let's understand. The electric field equals 0 because it cancels, because one force hits another force. So that's sort of like saying the gravitational field surrounding me is 0 on my left and my right. It really isn't. It's just that they're opposite forces, one going left and one going right. So they cancel each other out. So it's, I don't like, it should be made clear that sometimes a 0 is a net product of canceling forces, not the absence of force. So the absence of something should have a different 0, like a 0 with a dot in the middle. There ain't none. Versus there is stuff, but it all works out to being nothing. It nets out to, 3 minus 3. It wasn't 0 plus 0 equals 0. Yeah.
And it means there is some crazy conspiracy of all these charges that are uniformly distributed here, which each individually contribute to the electric field inside through Coulomb's law, that all those together, through a conspiracy, make the E field everywhere inside 0. It's a non-trivial result. All right, so now...
And I don't know if he's going to explain it, just as I did, that it's a result that's the product of a kind of understandable physical circumstance, where as you move any direction, you change your exposure proportionally. And so you're always got the same amount of, it's not the same volume of pi. Let's see how to say it. The force is always going to be the same, because even though you're getting hit by weaker stuff from behind, there's more of it. There's more snowball throwers that you're exposed to from behind, even though they're further away.
Now we know that the E field inside is 0. So this is for R smaller than R. Let's now go R larger than R.
So
everything
inside,
I told you holds for the
now
sphere,
we're going
which is
outside.
outside this hollow sphere. Everything holds. The E field here must be the same everywhere on the surface. The A and E are either parallel or anti-parallel. So I can write down again that 4 pi R squared, which is the surface area, times the electric field vector, must be the Q inside divided by epsilon 0. But this Q is that Q. It's not 0. There is charge inside. And so now I know that the electric field E, in terms of its magnitude, is Q divided by 4 pi R squared epsilon 0.
Alright, so he's basically now said the density, so that in a sense it holds true. The bigger you make the outside box, the more diminished the force becomes, because you're spreading it over a bigger surface. So it's still symmetrical, and it just becomes weaker based on the increase in the size, which is the same as the inverse square law. So I don't know why they just don't say it's the inverse square law. Curious.
And we know the direction. If it is positive, of course it is radially outwards, and if this is negative, it's radially inwards. And this is a non-trivial result. We have seen this before. If I had put all the charge...
Yeah, I think you can just get rid of the 4 pi and the epsilon 0. I mean, that's a constant anyway. And just recognize that Q gets smaller by the inverse square law. I mean, why? I don't, I don't get it exactly.
Charge right here at the middle, at the center, we would have gotten exactly the same answer. We've seen that before. In other words, whether the charge is uniformly distributed over a sphere, or whether the charge is all of it exactly at the center of the sphere, that makes no difference for the E field as long as you're outside the sphere. If you plot the electric field as a function of R, and if here is capital R, and if this is the...
And again, it's this totally dependent on this idea that your tiny point charge, you know exactly what shape it is. But we know that, generally speaking, they function as spheres.
The field strength, then you would get that the electric field is 0 inside, jumps to a maximum value, and this falls off as 1 over r squared, proportional to 1 over r squared.
Now, that makes sense. So, yeah, get rid of all the other 4 pi stuff and the epsilon 0 stuff, and just recognize that the the force inside is nothing, because it all cancels. All right, the net is nothing. And then it's on the outside, it's strongest right on the surface, and it, you know, depending on how big your balloon is, and it diminishes as you go away from the surface.
If I go back to the situation that the charge, that the electric field inside is 0, you may say, isn't that a little bit of a cheat? Because, yeah, there is no charge inside, but have you really used the charge outside? And if you have used it, how did you use it? Well, I have used it. I use it through my symmetry arguments. The symmetry arguments take into account that the charge is uniformly distributed. If the charge on the sphere had not been uniformly distributed, I could not have used the symmetry argument, and therefore the electric field inside would in fact not have been 0. If there is more charge on the sphere here than there is there, the field inside the sphere is not 0.
But obviously that would be impossible with gravity, or it would be impossible with just about anything. You just can't. All of these things are radial forces, so they're not going to have an uneven charge. But if you put like a dipole inside, then you're going to have a problem, because you're going to have more of one kind of force on one surface than another kind of force. Or if you put a hole in the sphere, yeah, the hole is not going to work anymore. It's going to break. That hole will create gravity on its edges, and it'll create a whole bunch of weird crap on the edges.
So I have used all that charge by using my symmetry argument. Gauss's law and Coulomb's law in a way are the same law. They both link the electric field with the charge Q. Key is the fact.
So again, it's a magnetic field. It's just not appropriate to call it an electric field. Electricity is the idea that the atom has pressure, and that pressure can be transferred. That's electricity. The pressure is doing this thing. Okay, it's making the big thing look neutral and then changing the size. I bring it in, I have now created an ion in sense. I bring it out, I've created an ion, an unevenness. This one gets bigger or smaller based, and it goes through a neutral. So the ground is the neutral, this is the change, is coming closer and further. And that changes what the atom radiates net. What it radiates is a force, whether it becomes a positive or a negatively charged object, and how charged it will be is that distance. The closer I bring the electron, the more charged it is. The closer to neutral, the weaker the charge. Then I switch the charge sign as I go past. So it's like the focus on a lens, you know, where they cross. You know, there's a neutral point, and inside that you have real images. Outside that you have projections. Some other word for it. But that's really what's going. And the force is magnetism. It's this red and black. It's this. You become electron heavy in your in what you're excreting to the world, or you become proton heavy in what you're excreting. And you can sort of intuit this by recognizing the closer the electron is, the more force it's blocking. If you could think of it as blocking, the more light. It's like the sun and the earth. If I put this earth really close to the sun, it casts a big shadow, and so the sun is sort of diminished. If I put the earth further away, because the sun's rays are diverging, this earth will block fewer of the rays, and so now the net out here, the light that gets to the rest of the universe, is increased. So the further away I put the earth, the more the universe says the sun is brighter. The closer I put it, the earth, the more the universe says the sun is diminished. It's weaker. Spacebar.
That the electric force falls off as 1 over r squared. If the electric field strength did not fall off as 1 over r squared, Gauss's law would not even hold, and the electric field inside this uniformly charged sphere would not be 0. So it is the immediate consequence of the fact that electric forces fall off as 1 over r squared.
So he's basically just pointing out the argument that if you're exposed to more stuff and it doesn't r squared, that is, like when you're on one side of the circle and you're really close to the inside surface, if it didn't diminish the force from that greater circumference of the circle at the r squared and it stayed stronger, then obviously you'd be pulled, towards the other surface. So the reason why your gravity is neutral is because that force is weaker and you're exposed to more of it.
Gravitational forces also fall off as 1 over r squared. Therefore, if you take a planet, if it existed, which is a hollow spherical planet with hollow insides.
Let's understand that anything that has spherical symmetry, anything approaching the shape of a sphere that radiates a force evenly is r squared. So it just doesn't matter what it is. As long as it's not a dipole where it's got another one I'm stuck right on it that's doing the opposite. But if you have a clear space, it's true for light bulbs. It's true for all light. And the light reflecting off my hand is doing the same thing. It's shooting light in all directions forward of my hand. It's not shooting light backwards. So it's shooting light in all directions, really strange angles. In all directions, each little atom is interacting with a photon, and when the photon leaves, it can leave going straight back, or it can leave going that way, that way, that way, that way, all these other directions. And that's sort of why mirror images are kind of dull. They're not very bright. They're not as bright as reality. They're not as not as high contrast. Is because the amount of light that hit my hand, a lot of it isn't going back to the mirror. A lot of it's going that way and that way and that way. I can see my hand from all kinds of other angles that aren't the image I'm looking at, because my hand is creating images essentially in all these other directions. And there's, and that's the r squared. So my hand, I go half the distance. So my hand is this big. I go half the distance. It's 4 times smaller.
It means there would be no gravitational field inside that hollow planet. So if you were there, there would be no gravitational force on you. If it is spherical. If that planet were a cubical planet, then the gravitational field inside would not be 0. You say, well, big deal. With eta 1, we always take a planet, and then as far as we're outside the planet.
It sort of would have been interesting to show that example, just to point out that The difference would be in just the corners. The corners would be what would be messing things up. So the flat surface and flat surface would be okay, and the flat surface and flat surface would be okay, and the flat surface and flat surface would be okay. But the corners is where everything would go wrong.
We put all the mass and we consider it as a point. Yeah, indeed. It's not a big deal for you, and it's not a big deal for me, but it was a big deal for Newton. He intuitively sensed that it was correct, that if you have a planet of uniform mass distribution, that you can consider it as a point mass, as long as you're outside the planet.
So again, that's just doing the spherical thing. Calling it a point mass is you're just saying it's radiating force in all directions. I don't think Newton did anything all that brilliant except start to think about light emanating for something. I think he thought about the ray image. Okay, rays were drawn in artwork thousands of years ago, and all you have to do is think about those rays, and you'll start to think about, well, you get hit by a lot more of those little rays when you're close to it, and you get hit by a lot less of those rays the further away you go. And what he's really just kind of figured out that, well, if I draw it flat on a piece of paper, right, a bunch of rays, well, that's not really reality, because reality is 3 dimensions. So he could see, so he figured out, what it seems kind of obvious, that the rays diverge. There's a bigger distance. That means there's less of them are going to hit you out here than they'll hit you in here, and that works in both directions. Squared. So that's the square part, both directions. That's the 2 part. You can't just think of it 2-dimensionally. That's not squared. That's not, that's just doing 2 squares. You have to think of it 4 squares. 1, 2, 3, 4. So I'm just saying, Newton did good, but the R squared part, theoretically, somebody should have thought of that a long time ago, because frankly, it's almost obvious if you think of the force as being straight line rays. If you think of the light as being straight things moving in a straight line, whatever the thing is, I don't care whether you think it's a wave perturbation-y thing or a coaxial cable or whatever you think it is. If it's moving in a straight line and it has a tiny profile, and there's a bunch of them, like I said, the inverse square law is just kind of obvious for round things.
But it took him 20 years to prove it. And he finally published his results. It would take us now 30 seconds. He didn't have access to Gauss' law. It came about 100 years later. But the net result is that you see here in front of you.
So again, I mean, you don't really need Gauss's law. All you need is to draw it on a piece of paper and then say, oh yeah, that's 2 dimensions, let's make it 3. And you got it. It's an easy model to make. I mean, take a round piece of styrofoam, stick wooden sticks in it. Okay, and then just measure the distances, and inverse square law. There it is again. It's there. So that's all you really need is a model. Just stick sticks in a piece of styrofoam, and you can figure it out.
If you have uniformly charged distribution, and you can draw the parallel with gravity, that you get the same electric field outside that you would have gotten if all the charge is at one location, at the center. This is
so he's just saying that the average would be the average at the center. So you just take this, and this, figure out their total charge, put it at the center, you're done. I mean, that's again not too complicated.
Spherical symmetry, number 1. That's the easiest symmetry that we have in 802. Now I will present you with a second form of symmetry, which is a flat horizontal plane.
All right, well, maybe we'll call this part 1, and continue some point in the future, which isn't here yet, and which you can't get to. And when we're there, when that does happen, you won't be able to get back here. It just won't happen. Let it go. A little commentary. Anyway, so I just have to hit a button of some sort, and that should be it. So till the next time, thank you for your attention.